Cambridge AS Chapter 4, Processor Fundamentals, Part 1. We will start studying the processor fundamental. What is that processor? The processor is the central processing unit, which is the brain of the computer. Okay, this is the heart of the computer. We will study its components. Okay, and then afterwards we will proceed to studying assembly language, and this is a low-level programming language. We will study it soon. Okay, let us start now with processor fundament. Okay, the von Neumann model of a computer system. This topic I am explaining is identical to the way it is taught in the O-level, in O-level computer science. It is just identical. I will explain it here with little bit fast. Okay? So the von Neumann, there was a scientist called von Neumann who invented the very basic computer model. That's why it is named after him. And you need to know this because it may appear in the exam. So the von Neumann model of a computer, the simplest form of what may be described as a computer system model or a computer system architecture is usually contributed to John von Neumann, and we call it the von Neumann model. Okay, it is him who invented the stored program concept. What is that stored program concept? Remember that we used to say a computer system consists of hardware and software. Hardware represents all components, the keyboard, mouse, input devices, output devices, the central processing unit, RAM and ROM. These are all hardware devices. Okay, programs run on these devices. So programs run on the CPU. A program is initially stored on the hard disk. So the program is initially stored on the hard disk. When you want to run a program, it loads first to the main memory RAM. Okay, so this is what is called a stored program concept. So the program is in the main memory. Let us assume that what we have here in memory is the program instructions. Those instructions are transferred to the central processing unit, or the CPU reads instructions from memory, instruction after instruction. So this is the first instruction at location 0, or you may say address 0. And then the next instruction in location 1 or address 1, together with the data. So in the memory, we have the running program together with its data. And then these instructions are moved, or we can say fetch. The processor, this is the processor, this is the CPU. The CPU fetches, we would like to use that term, fetches instructions from the main memory, instruction after instruction, putting it into registers inside of the CPU. And this ALU represents the arithmetic and logic unit. There is what is called arithmetic and logic unit. That arithmetic and logic unit, arithmetic means carries on all the arithmetic calculation, and logic means carries all logic operations. Okay, So this is the arithmetic and logic unit where instructions are executed, where data is calculated, and results written back to memory. Okay? And this is what is called a program running. So we fetch an instruction from memory. Again, the processor, the CPU fetches an instruction from memory, executes that instruction, and then fetches the instruction after one after another very fast. And this is what is called program running. Okay? So the program must be resident in main memory. Any program running must be in main memory. The program consists of sequence of instructions, as you may see here, which occupy a contiguous block. So instruction number 0, followed by instruction number 1, followed by instruction number 2. That's why we have a register here called program counter. We have a register called program counter. That program counter points to the current instruction and then is incremented to point to the instruction after it. Okay, so the program counter here, from the program counter address, the program counter shows the address for reading and writing the data. We may say this is the address bus and this is the data bus. We have to study buses. There are 3 types of buses: address bus, data bus, and control bus. We will study them all. Okay? Okay. The program consists of sequence of instructions in the main memory. Instructions and data are indistinguishable. These are all together instructions and data. The program knows what is the instruction and what is the data. Each instruction is fetched. Yes, I like to use this term. And I would like to use this sequence: fetch, decode, execute. The processor fetches an instruction, means copies it from the main memory to the processor. Decodes, which means interprets how to execute the instruction, then executes it, which means performs it. And then repeat again with the instructions that follow. Okay? Okay, so this is the von Neumann model of computer system, or stored program concept. The model has the following basic feature. There is a processor. The CPU is called the central processing unit. There is a processor called the CPU. The processor has direct access to a memory. We have address bus, data bus, and control bus, all connecting the CPU, to the main memory, the RAM. Okay, so the processor has direct access to memory. The memory contains a stored program and the data required by the program. Here in the memory, we have the program and its data. Stored program consists of individual instructions. Processor executes instructions sequentially. Okay? Okay, let us study this again. The central processing unit shown below is a simplified schematic diagram of a processor that could be part of this simple system. This is a very much simplified model of of what we may call a computer system. The dotted line shows the boundary of the processor. Anything inside this dotted line is inside the CPU, the central processing unit. Okay, the logical arrangement of some of the processor component is indicated. Arrows show possible directions of flow of data. To be honest, I copied this diagram from the O-level notes or from the O-level textbook. So if you like to refer to the O-level and revise that chapter, it would be very useful. Okay, let us try to explain. We have here address bus and data bus. The address bus sends the required address to the main memory. The data bus sends or receives data from the main memory. That's why the data bus is bidirectional, because it may send data to the main memory or it may receive and read data from the main memory. That's why the data bus is bidirectional. Here, the address bus is unidirectional. Why? Because it is always the processor, or to be specific, the program counter or the control unit that decides the required address. So the address bus is unidirectional. The data bus is bidirectional. How many buses do we have? They are 3. This is the address bus, this is the data bus, and this is the control bus for carrying control signals. Okay? What components? So we told about the 3 buses: address bus, data bus, and control bus. The control bus is bidirectional because it sends or carries control signals to components, and then it receives interrupts. You have to study about that, called what is called interrupt. It receives interrupts. When a device requires the processor attention, it sends an interrupt signal along the control bus. Okay? What else do we have? We have system clock for synchronizing all the timings and providing the timing signal to synchronize everything inside of the CPU. Anything inside that dotted line is inside the CPU. We also have the control unit. The control unit controls, it is called the control unit. The control unit controls everything inside of the processor, inside of the computer. It even controls the address bus, the data bus, the control bus. It even controls the main memory. The control unit controls everything. The arithmetic and logic unit is there to calculate and compute everything. All arithmetic operations are done in the arithmetic, and all logic operations are done in the logic unit. Arithmetic and logic unit, ALU. Okay? Now let us look at those orange boxes. They are called registers. They store values. Let us study them. They are 5. You have to study them by their names. And also you have to know what is the duty of each one of them. Okay? Let us start with the program counter. The program counter contains the address of the next instruction. So it contains an address initially pointing to the first instruction, and then every time it is incremented by 1. That's why we call it program counter. It counts. So the program counter contains the address of the next instruction. And the address from the program counter goes to another register called memory address register, MAR. The the address in the program counter is transferred to a register called MAR, memory address register. And that memory address register is attached to the address bus. So the address bus is there to carry the address. The required address initially comes from the program counter and is copied to the memory address register and goes to the address bus. When it goes to the address bus, it reaches the memory. Then the required data comes along the data bus and is stored initially in the memory data register, MDR. Stored initially in the memory data register, MDR. Okay? And then copied to the current instruction register. The current instruction register is directly connected to the control unit, because when the instruction arrives to the CIR, current instruction register, it is already inside the control unit, and the control unit decodes that instruction and executes that instruction. Okay, so we told now about 4. Program counter copies its data into the MAR, memory data register. So the memory address register is directly connected to the address bus. The memory data register is directly connected to the data bus. Data comes and stays first in the MDR, memory data register, and then copied to the CIR, current instruction register. Only one left, only one register is left. That is called the accumulator. The accumulator is inside the arithmetic and logic unit, and the ALU is performing all necessary arithmetic and logic operations. And the values being computed, or the results of computation, will be in the accumulator. I think I told the whole story. I think I told about all the components in here. I hope it is understood. Okay, let us read these lines. It may clarify more what we want to study. The program counter, this is the program counter, holds the address of the next instruction to be loaded. The program counter holds the instruction of the address of the next instruction. So the program counter holds the address of the next instruction to be loaded. This address is sent to the memory address register, MAR. So the address from the program counter goes to the memory address register, MAR. The memory address register, MAR, is directly connected to the address bus. Okay, so when the address goes to the address bus, it goes directly to the memory, and the corresponding data comes along the data bus and stays in the memory data register. That's why we have here the memory data registers holds the data fetched from this address. Actually, this will going to be called fetch, decode, execute. And this is the heart of running a program. Okay? The data is sent to the current instruction register. The instruction comes from the memory data register and goes to the current instruction register. And when the instruction goes to the current instruction register, it is already inside or very close to the control unit CU. The control unit decodes the instruction, interprets or understands the instruction here. The data is sent to the current instruction unit, and the control unit decode the instructions opcode. The program counter is incremented so that afterwards it points to the instruction that follows. Okay? Just study these. I think I have seen questions complete questions. I think it is something very similar to that. The control unit transmit the signal. So we have here the control bus. The control bus transmits signal to coordinate events based on the pulses of the system clock. Where is this is the system clock. So the system clock synchronizes, sends pulses to synchronize or coordinate all activities. The data bus, this is the data bus, or this is the data bus, carries out data to components, while the address bus carries addresses where this data is being written to or read from. It is very simple. The address bus carries the address. The data bus carries the data. The arithmetic and logic unit, ALU, performs mathematical operation and logical decisions. I think those sentences are quite common. You have to study MAR, MDR, PC, CIR, and other registers. Refer here to the accumulator. You have to study these 5 registers very well. And the control unit and the arithmetic logic unit and the system clock, plus the 3 buses. We will be talking about these over and over until everything becomes clear, inshallah. Components of the CPU. These are the components of the CPU already told. The 2 major components of the CPU are the arithmetical logic unit, this is the ALU, and the control unit, this is the control unit that controls everything. The ALU, which is the arithmetic and logic unit, is responsible for any arithmetic or logic processing that might be needed when a program is running. The functions of the control unit are more diverse. The control unit has to do many other things. One aspect is controlling. The control unit controlling the flow of data through the processor and through the whole computer. Ensure the program instructions are handled correctly. Okay, so this is the internal component of the CPU. Let us look, please, let us look at exam questions because they repeat the same ideas and hopefully it becomes clear. Okay, please go to my classified and please open page 163 and please complete this. I will give you a minute. So in page 163, the processor has one general purpose register, the accumulator ACC, and several special purpose registers. You should know the program counter, the MAR, the MDR, the CIR. They are 5. One of them is the accumulator ACC. The other I have just mentioned. Program counter, memory address register, memory data register, and CIR current instruction register. Okay, complete the following descriptions of the role of the registers in the fetch execute cycle. And now they call it fetch decode execute. What does this mean? This is the most important item of activity, the fetch decode execute. Fetch an instruction from memory, puts it in appropriate registers in the CPU, decodes that instruction, and then executes that instruction, and then look for the instruction that comes next. So look here, the program counter hold the address of the next instruction to be loaded. The address is sent to the memory address register MAR. Plus, يبقى the address the address is sent to the memory address register MAR. The what hold the data fetched? The memory data register MDR holds the data fetched from this address. This data is sent to the current instruction register CIR, and the control unit decodes the instructions. Opcode. Next, the program counter is incremented by 1 to point to the instruction after. Okay? If you know this, you may earn 5 marks. Easy marks. Okay? Go to the next page. You have to read those descriptions. Let us go to this page. Let us go to page 165 first. Somebody uses a computer for work. Complete the following descriptions of internal components of a computer by writing the missing term. The what transmit the signal to control events based on the electronic pulses of the. I think the clock is creating electronic pulses. So the clock, or you may specifically call it the system clock. So I think the system clock generates timing signal, and I think the control bus. So we may write here, the control bus transmits the signals to coordinate events based on the electronic pulses of the system clock. The what carries data to the components, while what carries address. I think the data bus carries data, while the address bus carries the address. The what performs mathematical operations. It is the arithmetical logic unit that performs mathematical operations. I hope these are clear. So we have here another question, page 163. The control bus transmits signals to coordinate events based on the electronic pulses of the system clock. So the control bus transmits signal to coordinate events based on the electronic pulses of the system block. The data bus carries data. It is so simple. Data bus carries data, while the address bus carries address. The arithmetical logic unit performs mathematical operations and logical. Okay? Let us talk then about that number of core and more. Okay, there are two major components of the CPU, the arithmetic and logic unit, ALU, and the control unit. The ALU is arithmetic and logic unit is responsible for any arithmetic or logic processing that might be needed when a program is run. The functions of the control unit are more diverse. controlling the flow of data through the processor and through the whole computer system. Another is ensuring that program instructions are handled correctly. Processor type and number of cores. Multi-core processor. What I am telling you now is about a single core processor. This is just a simple processor. However, nowadays they have a processor that have several cores of these. So these we call it a core. So we have several cores working in parallel, so the performance of the processor would be better. Okay? So the multi-core processor is a computer processor on a single integrated with two or more separate processing units called cores, each of which reads and executes program instruction. So we may have dual core processor or quad core processor. Each one has its own CPU, its own registers, and working in parallel with others. So if you have quad core processor, means you have 4 CPUs running in parallel. You may have something like 4 times faster speed. Okay, so the speed is increased 4 times. So you have what is called a core, and the core is the CPU and its register, each of which reads and executes program instruction. The instructions are ordinary CPU instructions, such as add, move, and branch, but the single processor can run instruction on separate core at the same time, increasing overall performance and support multi-threading, so you run programs in parallel. Okay, so this is the number of cores. A core is a CPU together with its registers. The number of cores can affect the performance of the computer. Each core processes one instruction per clock pulse. More cores mean that sequences of instructions can be split between them, and so much more than one instruction is executed per clock cycle. So if you have quad core, it means 4 processors, you can execute 4 instructions in one cycle, okay, per clock pulse, and more sequence of instruction can be run at the same time. More cores decrease the time taken to complete a task because the processor will be faster. So if you want to enhance the performance of the processor, use dual core, multi-core, quad core, multi-core processor. Also, the clock is important. If you increase the clock speed, things will be done faster. The clock generates the timing signal to synchronize events in the processor and the fetch, decode, execute cycle. We will study it very well, that fetch, decode, execute cycle. We already told about it several times. The clock sends out a number of pulses in a given time interval, clock speed. Each processor instruction takes a certain number of clock cycles to execute. The higher the clock frequency, so when the clock goes faster, the shorter the time is taken. Increasing the clock frequency improves performance. So if you have higher clock speed, you get better performance. If you have more cores, you get better in performance. Okay, so what is that clock speed? The clock speed determines the number of cycles the CPU can execute per second, because every clock pulse can do one fetch, decode, execute cycle. If you have a higher pulse rate, which this means you may have more instructions done per second. However, you cannot just increase it the way you wish. There are limitations. If you increase it beyond its limit, things will get out of synchronization and the computer may heat up and then fail. Okay? So increasing clock speed increases the number of operations and the number of fetch, decode, execute cycle that can be performed by unit. However, there is a limit on the clock speed because heat generated by higher clock speeds cannot be removed fast enough. You cannot just make the clock faster and faster the way you wish. There are limits. Okay, so this is the clock and the clock speed. Registers, what are registers? They are 5 registers. Let us read them again. There are 5 registers. The current instruction register is inside or connected to the control unit and holds the instruction being performed right now. The accumulator is another register very close or inside the arithmetic and logic unit and holds the numbers being calculated right now. So the CIR carries the instruction, the accumulator carries the intermediate or the final result of calculation. Okay? We know that the memory address register, MER, is just connected to the address bus. We know that the memory data register, MDR, is just connected to the data bus. We know that the program counter holds the address of the next instruction. So the cycle goes like this. Again, let us say now the fetch cycle. The program counter contains the address of the next instruction. The program counter is copied to the memory address register. The memory address register takes data through, and I'm sorry, takes the address through the address bus. And then the corresponding data comes through the data bus. And it stays for a minute in the memory data register and then may go to the CIR current instruction register if it is an instruction. If it is an operand, which means it is some data to be calculated, it goes to the accumulator ACC where calculations are carried out. Okay, they are 5 registers. Study them. Study them before they become more than 5, because in the AS we have to study few more registers. So the other components of the CPU are the registers. These are storage components which, because of their proximity to the ELU, allow very short access to it. A register is either a general purpose or a special purpose. The general purpose, there is only one general purpose register referred to as the accumulator, ACC. They call this general purpose register, the accumulator. Why? Because they use it quite often in any mathematical operation or logical operation. Okay? General purpose register, there is only one general purpose register. It is referred to as the accumulator. General purpose register, there is only one general purpose register. It is referred to as the accumulator. However, special purpose registers, we know 4 of them from the O level. The table below shows some of the special purpose registers as individual component. Okay? Okay, those are the special purpose register. We have the CIR, current instruction register. Store the current instruction while it is being decoded and executed. We have the MAR and MDR. The MAR is connected to the address bus and the MER is connected to the data bus. The PC program counter stores the address of where the next instruction is to be read from. And this is the one that will be incremented by 1. We have 2 new registers newly introduced in the AS. One of them is called the IX, the index register, and the other is called the SR, the status register. The index register will be used in the addressing modes. We will not explain the addressing mode right now, so keep the index register for a while. The index register stores a value that only used for indexed address. We will study the indexed addressing next, so let us keep the IX for a while. The status register is very simple. Let us explain it right now. The status register is interpreted as individual bits. It may have like 8 bits, each bit indicating one state. Each bit or flag is set. Set means becoming equal to 1 or reset becomes equal to 0. يبقى each bit or flag is set depending on an event. For example, addition overflow. If you know what overflow is from the O level. If you add 2 numbers and the result is greater than the available number of bits, overflow occurs. And then there is one flag in the status register that is set to 1 when an overflow occurs. Or there is another one when the result of operation is 0. So you have, this is the status register, and you have several bits, each one carrying a flag, yes or no. For example, 0, carry, negative, overflow, and things like this. So these are the special purpose register. Immediate access store, IAS, we have what is called cache memory. The cache memory is inside of the processor, holding frequently used instruction. The cache stores commonly used commands so they can be reused more quickly than reading from the RAM. The RAM is very fast, but we want even faster access time. Immediate access store is used by the CPU to store data waiting processing, so it is instantly accessible. Then we have bus, and this is called level 1 cache and level 2 cache that represent the immediate access store. Let us study this example. Current instruction register connects to store the instruction that is being decoded and executed. Memory address register connects to store the address. So it is memory address register. So it stores the address of the memory location about to be written to or read from. Program counter stores the address of the next instruction. The memory data register MEDR store the data that has just been read from memory or is about to be written to memory. So these are the registers we have. Buses, we have 3 buses. We have 3 buses: address bus, data bus, control bus. The sole function of the address bus is to carry an address. So we have an address bus, and it is only there to carry an address. The address bus is a component that carries an address to the memory controller to identify a location in memory, which is to be read from and written to. So the function of the address bus is to carry an address. This is the address bus. Okay, the CPU decides the address, and the address goes to memory, or the address goes to input and output storage, even for reading and writing, both the same. What about having more bits? The width of the address bus. These are the new bits of information in the AF, because you should know the address bus from the O level. Increasing the address bus width, which means the number of bits, because the address bus is using parallel transmission. Increasing the address bus width from 16 bits to 72 bits significantly increases the number of directly addressable memory location. So when you have 16 bits, the address location, number of address locations is 2 to the power of 16. However, when you have 32, it is 2 to the power of 32. So it's a rise in the exponential. So it increases so much. So if you have more bits in the address bus, this means you will have bigger memory. The data bus, the function of the data bus is to carry data. Width of the data bus. If you have double the width of the data bus, you can transfer double the data than not with when the width is doubled, the number of bits transferred is doubled. So width of the data bus. The width of the data bus determines the number of bits that can be simultaneously transferred. Increasing the width of the data bus increases the number of bits that can be moved at once. Here, the increase is not exponential. With increasing the width of the address bus, the increase in memory size is exponential. Here, it is not exponential, it's just linear. Okay? For example, double the width of the data bus moves twice data per clock. So this is the address bus, the data bus, and then the control bus. The control bus transfers a signal from the control unit to all other system components, or transmit a signal to the control unit when it's an interrupt signal. Let us solve this. Receives data from the MAR. This is the address bus. The address in the memory MAR, the memory address register, goes to the address bus. To receive data from the MAR, this is the memory address register. Carries an address for an instruction or a value. This is the data bus. Transmit timing signal to component. This is the control bus. Bidirectional, the control bus is bidirectional, the data bus is bidirectional. Do you remember the USB Universal Serial Bus? Okay, do you remember the USB? We studied in the O level. It is plug and play. When you connect a USB, it is automatically detected. So the plug and play concept was only fully released by the action of the USB Universal Serial Bus Standard. The USB standard, a hierarchy. This is typical in the O level. The USB standard, a hierarchy of connection is supported. The computer is at the root of this hierarchy and can handle 127 attached devices. you can plug a CPU, a USB. From it, you can generate 4 or 5 other USB ports. Devices can be attached while the computer is switched on and are automatically configured. The standard has evolved since USB 3 is the latest version. Can be synchronous or asynchronous. Transfer can be full duplex, which means send and receive both at the same time. So this is the USB and universal serial bus. Advantages of USB, all of this is just O-level. Devices are automatically detected and configured when first attached. This is known as plug and play. Impossible to wrongly connect a device. USB has become an industry standard and supported by many operating systems. USB 3 allow full duplex data transfer. Slower versions are backward compatible with earlier versions. Later versions are backward, so you may operate USB 3 with an older version USB 1. Allow powers to be drawn to charge portable device or power a mouse. Okay, so this is the universal serial bus USB, and it is all like this in the O-level. We also have video graphic cards Vega. This used to be used to connect televisions and monitors, analog monitors. However, now things are getting digital and monitors are connected using HDMI. In old days, we used to use Vega, VGA, Video Graphics Array, is a video display controller and first introduced with IBM, which become in PC industry. Okay, so this is a Vega connector. We will see questions about it in recent exam. This is more popular now. The HDMI, high definition multimedia interface, can carry high definition TV signals together with audio. Audio video interface for transmitting uncompressed video data and compressed or uncompressed digital audio from an HDMI compliant source, such as a display controller or a monitor. HDMI is digital replacement for the analog video standard. So that used to be analog. The Vega used to be analog. Display port these sockets are called display port. This is HDMI, this is display port. Digital display interface, developed by the consortium of PC and chip manufacturers and standardized by the Video Electronic Standards Association. Connect a video source to a display device, such as a computer monitor. So it connects a video source. It can also carry audio, USB, and other data. Okay, we will stop here. We cannot go further. However, there are many things to solve here. Okay, let us do this. Describe the ways in which the following factors can affect the performance of his laptop computer. Number of cores. Each core processes one instruction per clock pulse. Multiple cores mean that sequences of instructions can be split between them, and so more than one instruction is executed per clock pulse, and more sequences of instructions can be run at the same time. More cores decrease the time taken to complete tasks. Okay? Another question. What is the effect of the clock speed? Each instruction is executed on a clock pulse. One fetch execute, or now called fetch decode execute cycle, is run on each clock pulse. So the clock speed dictates the number of instructions that can be run per second. The faster the clock speed, the more instruction that can be run per second. Okay? So please go and solve all these. Memory address, register, memory data, the purpose of the system clock. Okay? Okay, we will stop here. We will do the fetch, decode, execute cycle next, but we already talked about it. We already told about it. Interrupts, interrupt handling, and then the new part that is machine code instruction, addressing mode, and then assembly language instruction. Okay, we keep this for later. Please study that part very well. Up till now, we didn't say much more than what is told in the O level. Thank you very much for your attention.